Next we will discuss on scan architectures. Now, as I have said that in a sequential circuit, to test for the sake of testing it, we convert it into scan circuit. Now, there may be choice in the sense that we may decide that all the flip flops will be converted to scan flip flops, or another option may be that only a subset of the flip flops are converted into scan flip flop, and also in the access pattern by which we can access those individual flip flops. So, in a full scan design, almost all storage elements are converted into scan cells, and then combinational ATPG is used for test generation. So, here all the flip flops that are there in the design, so they are converted to scan flip flops. So, now for the test generation purpose, since we can control those flip flops externally, so I can have a pure combinational test pattern generator to generate tests for the combinational part, and these flip flops can be tested beforehand by applying some shifting pattern through this flip flop to this flip flop chain by maybe all 0, all 1, alternate 0, 1, like that we can apply a few flush patterns and get the confidence that the chain is working fine. Other possibility is that only a subset of storage elements are converted to scan cell, and then all flip flops are not converted. There may be logic behind this, because as soon as we convert a flip flop into scan flip flop, so in most of the cases some multiplexer get introduced. As a result, the delay of the design may go up. So, there may be some flip flops which are critical, so we cannot convert them into scan flip flop. So, they continue to remain as normal flip flop. So, what happens as a result is that we get a partial scan design. So, in partial scan, a subset of flip flops are converted into scan. So, naturally now we have to use a sequential ATPG. So, because now the circuit still remains a sequential circuit. So, a sequential test pattern generator has to be used for generating the test sequence. Now, once we have converted the flip flops into scan flip flops, the connection pattern between them, so they can define the access pattern. So, if all the flip flops are put on a chain, then the way to access these flip flops is through a serial mechanism. So, it is a serial scan chain. So, on the other hand, there may be these scan flip flops may be organized in a 2-dimensional way, and then I can address these individual flip flops by means its row address and column address, giving a random access scan architecture. So, in the successive slide, so we will be looking into these architectures. In full scan design, all storage elements are replaced with scan cells. So, what happens in the design is that if I have got in the design a number of primary inputs, and a number of flip flops are there. So, what happens is that these flip flops are converted into a scan chain. They are converted into scan chain. From the outside through the scanning line, we can input the pattern into these flip flops, and there is a scan out pin. There is a scan out pin by which the content of these flip flops can be checked, and these are the primary output lines. So, what happens is that for the testing purpose, so I can consider these primary inputs as well as these flip flops as primary input. So, all of them can be configured, can be viewed as primary input. That is why all inputs can be controlled, and at the same time all outputs can also be observed, because the primary outputs are observable and these scan cells are also observable through scan out point. So, advantage is it converts a sequential ATPG to combinational ATPG. So, this test pattern generation problem becomes simpler. So, it is no more a sequential ATPG. Then there is almost full scan design, in which a small percentage of storage elements are not replaced with scan cells. So, this is for performance reasons, because as I have already said that some of these storage elements may be on the critical path of the design. So, if we put them on the if we modify to scan cell, then the delay may be a problem. So, another issue may be the flip flops location. So, if it is located haphazardly through it is far away from, if some flip flop is far away from other flip flops, then when doing the scan stitching and making the scan cell, then I have to have a long wire running from this cluster to that isolated flip flop to put it onto a chain. So, that also sometimes may be undesirable. So, that is the reason. And so, also the clock distribution is another issue, like storage elements driven by a small clock domain that are deemed too insignificant to be worth the additional scan insertion effort. So, if the clock domain is very small, so what happens is that in any VLSI design, if this is the full chip, so it is divided into some regions. So, each region may be guided, it may have its own supply voltage V and the frequency of operation F. So, say this region is running at frequency F1, this is at F2, this is at F3. So, in some sense I can say that the clock for this region, clock for this region and clock for this region, they are different. Now, if we see that in F2 there is only very insignificant portion of the circuit that is put there in F2, then it may be better that we do not consider it for scan design. The reason being that that may be doing some very insignificant part of the job. So, for the testing purpose, so we may omit that part. So, as a result there is no necessity to put it onto the scan chain, that will unnecessarily lengthen the scan chain and create other problems. So, sequential circuit. So, suppose this is a sequential circuit. So, where we have got 3 flip flops FF1, FF2 and FF3, and then we have got this combinational logic. Similarly, so these are X1, X2, X3 are primary input, Y1, Y2 are the primary output. Now, what happens is that in a masked full scan design, these flip flops 1, 2 and 3, they will be replaced by 3 masked D scan flip flops SFF1, SFF2 and SFF3. So, this is the representation. So, you see that, so design of this scan flip flops we have seen beforehand. Now, as far as this combinational logic is concerned, so it has got X1, X2, X3 as input, plus these flip flops are outputs are coming as input, that is a pseudo primary input. Similarly, it is generating this primary output and pseudo primary output. Now, since these scan flip flops are put on a chain, so I can control these values that are coming into these individual flip flops, and that way I can control the value that should go to PPI. So, whatever for testing this combinational logic for a particular fault, we need some specific bit pattern in X1, X2, X3 and some bit pattern in PPI lines. So, those can be done, because through this scan chain I can shift appropriate pattern onto these flip flops. As a result, this combinational logic testing can be facilitated. So, I do not need to bother about how to initialize these flip flops to the patterns needed at the PPI input. Similarly, for the if this combinational logic test pattern that we apply, so it reflects the faulty output at Y1, then it is fine. So, we directly observe it. It may so happen that the faulty output comes in one of these PPOs. So, if it comes in one of those PPOs, then in the next cycle, when the shift when this is captured onto this scan chain, then in the next next few shift cycles, so this content of these scan cells will be shifted out to SO. So, naturally that PPO is also become observable. So, that way the ATPG for this combinational logic becomes simpler by introducing this scan chain. So, primary inputs. So, these are the external inputs to the circuit, can be set to any required logic. Okay. So, that is because they are primary input, and say they are set directly in parallel from the external inputs. So, in this case these lines X1, X2, X3, so they are fed parallelly from the external world. Now, then there are pseudo primary inputs. So, these are the scan cell outputs, and it can be set to any required logic values by doing this scan shifting, and but this has to be done serially, unlike this parallel input, unlike this parallel primary input X1, X2, X3. So, this PPI setting has to be done via serial shifting. So, that time is necessary. Similarly, primary output. So, these are external outputs of the circuit, they can be observed very easily, and they can observe directly in the directly in parallel from the external outputs. So, all these outputs are anything that is reflected on PO line. So, they are seen directly. On the other hand, there are pseudo primary outputs. So, these are they are available at the scan cell inputs, and they can be observed, but of course observed through serial shifting of scan outputs. So, how do we apply this test pattern? Suppose I have got a test pattern where this test pattern is divided into two portions. So, this test pattern V1, it has got a primary input part and a pseudo primary input part. So, primary input part is say it is some value. So, it is not specified here, some 3-bit value may be there, and for the pseudo primary input, suppose the desired setting is 1 1 0. So, what is done? First, this shift enable is made high, made high, and the clock is applied. So, these are the 3 shift cycles. So, first we in the serial input we have put a 0. So, that after the first clock cycle the flip flops 1 gets the bit 0. Then at the next cycle at the serial input we put 1, and this 0 of the first flip flop shifts to the second flip flop, and in the third cycle this 0 comes to the flip flop 3, this 1 that we had introduced comes to flip flop 2, and in flip flop 1 this 1 is introduced. So, this actually now I have got this pseudo primary input bits having the proper values. Then this shift enable is disabled, shift enable line AC is disabled, and there is a hold cycle that is given, that is that utility we will see later. For the time being we just ignore it. There is a hold cycle. After that this a clock, another clock pulse is given. So, this is called capture, because at this time this value is held at the input, and this so this combinational logic it will evaluate this input, this V1, the primary input part, it can be set to proper values at any time up to this part, up to this point, up to this shifting point at any time. So, for the sake of simplicity we can assume that their V1 is set at the beginning of the shifting itself. So, now after that so this capture cycle, so one pulse, clock pulse is given in the capture cycle. In the hold cycle the circuit value, the combinational logic, it evaluates this input pattern and sets the primary output and pseudo primary outputs to proper values. Then in the capture cycle the pattern that we have, so that is actually captured onto the flip flop. So, that is in the capture cycle. In the capture cycle, from this combinational logic output, the bits the pattern they get captured onto these 3 scan flip flops through their data input line. Now, after that there is another hold cycle given, so that we can see the primary pseudo primary output, the first bit of the pseudo primary output we can see that it is this L. So, this is actually checked. Then for the next pattern we start shifting, say next pattern is V2, and V2, for V2 there is a primary input setting. So, that is not our concern. Say for it the pseudo primary bit is bit should be 101. So, this 1 is shifted at the first clock cycle. So, as a result this L that we had at flip flop 1, so that gets shifted to the second scan cell, and this H of the second scan cell comes to the third scan cell. As a result we can view this second scan output, okay. This FF2 output of previous corresponding to previous pattern is now observable. Now, in the next another shift pulse, another clock pulse is given with shift enable remaining high. So, now this 1 comes to the second scan cell, and then new 0 pattern that we have applied at the serial input. So, that comes into the first flip flop, and this L goes to the third flip flop. So, we can see the third flip flop. So, after this clock we have got all the 3 bits of this pseudo primary output shifted out, and we could see the values. Now, this pattern has got the loaded, this pseudo primary input part of V2 has got loaded. So, again one hold cycle is given, and then a capture pulse is given. In the hold cycle the combinational logic will evaluate the value, and then in the capture cycle the values that are computed at pseudo primary output. So, they will get captured onto the flip flops, and again in the next pattern V3 the current response LLH will be shifted out through the scan out line, and the next pseudo primary input part will get shifted into the flip flops. So, that way this testing operation will take place. So, we can find out that this circuit now operates in several mode, like in circuit operation type normal and the scan. So, if TM the test mode is 0 and this shift enable is also 0. So, in that is the normal operation. Now, that is a normal operation. So, the circuit operates in a normal mode. Now, if this test mode is 1 and this shift enable is also 1. So, that is called a shift operation. Now, the pattern will be shifted through the scan chain. Now, of course, the combinational logic, since it is a combinational logic, it will do some evaluations, but those evaluations are not meaningful. We are not interested in those calculations. We will only be interested when this shifting is over, and once the shifting is over, so we give a hold cycle. In the hold cycle, the value gets the combinational logic, it will evaluate the values, and then comes the capture cycle. In the for the capture cycle, so this test mode is made 1 and this shift enable is made 0. As a result, the values that will be there in the pseudo primary output will get captured onto the flip flop. So, that way this capture operation. So, we have got 3 modes of operation in this full scan design. One is normal mode, one is shift mode, and another is capture mode. So, they are identified by this setting of this TM and test mode and shift enable lines. Then comes this clocked scan full scan design. So, in a clocked full scan design, so we have got 2 clocks, as we said that there is a data clock and there is a scan clock. So, DCK and SCK. So, for the normal operation of the system, this DCK line will be, the clocks will be given to DCK, and SCK will remain permanently low, and for the scan part, or so this SCK line will be giving pulse, they will be given pulse, and this DCK part will be, DCK clock will be deactive. So, in a masked full scan design, full scan circuit, a scan enable signal AC is used. So, this is the so here we do not have any AC signal. So, that was there in the clock full scan design. In a masked full scan design, in clock full scan design, we have got 2 clocks, DCK and SCK, 2 independent clocks for shift mode and capture mode of operation. So, operation is now very simple, like whenever we want to do the shifting part of the pattern. So, this SCK pulses will be given and the values will be given onto this SI. So, that the values are loaded onto these flip flops, and then we give the DCK clock. So, that this data that is there in so this they will be, so combinational logic will evaluate these Q values and these PI values. Okay, that is the PPI values and PI values, and accordingly the proper values will come in Y or this Y1, Y2 and this PPO bits. And then when this DCK clock will be given, so this from this PPO lines the values will be coming into these flip flops to this DI line, the data input lines, and then after again that shift clock will be given, and when the shift clock is given, so these values will get shifted to the next place. So, when the SO output, so we can serially see the output, while the shifting in of next pattern will be going on parallelly. So, otherwise it is same, but only thing is that instead of a separate scan enable line, so we have got a separate clock line SCK. Next, we will look into this LSSD full scan design. In LSSD design, so we have got the output of output port plus L1 of the master latch L1 is used to drive the combinational logic of the design. So, in this case, so this L1 plus is used for driving the combinational logic. So, in this case the slave latch L2 is used only for scan testing. So, basically this in case of LSSD design, so we had 2 version, one is the latched version, and another is that we have one part is that this latch is driving the combinational logic, and the second part is that for the shifting, so we need double latch. So, that is actually done by this L2. So, this L1, so this combinational logic produces some output that is latched here, and this latched output is going to combinational logic 2 as input. So, that is the basic circuit design that we have. Now, to handle this scan shifting part. So, this scanning line is coming and this L2 plus line is driving the input of the next one input of the next latch. Okay. So, similarly, this L2 plus line, so this drives the next latch. So, this way this SI line and L2 plus lines, so they will construct the scan chain. Okay. And this part, so this L1 plus line, so they are used for driving the circuit. So, this L1 plus line drives this circuit and this L1 plus line drives this circuit. So, this is from the design of the circuit. So, we do not have anything to design at this point, because that was the way the circuit was designed. So, it had two part, logic 1 and logic 2, and these flip flops. Okay. These latches were there, where this L1 plus and L1 plus. So, they were driving the two different combinational logic portions. So, if we are having a double latch design, so double latch design, here the combinational logic that we have, so there L1 plus lines are not used, but L2 plus lines have been used in the original design. So, in this case we have got this L2 plus lines feeding this combinational logic, and at the same time this L2 plus logic also forming the scan chain. So, there is no problem, because now these L1 plus lines are not required. So, in the previous case L1 plus lines were required for driving the combinational part, but here it is not required. So, in normal mode of operation, C1 and C2 clocks are used in a non-overlapping fashion. So, C1 and C2 clocks are used in non-overlapping fashion, so that the data that is coming to the first latch is shifted to the second latch, and then it is available at the for operation in the combinational logic. So, during shift operation we will be using clocks A and B in a non-overlapping manner. The scan cells SRL1 to SRL3, they will form a single scan chain from SI to SO. So, for this C1 and C2, so they are used in for normal operation in a non-overlapping fashion, and this A and B, so they are used in non-overlapping fashion for scan shifting. And similarly, during capture operation, this C1 and C2, they will be applied to load the test response from the combinational logic. So, that way they are remaining same. So, double latch design. So, if your system requires a double latch design, then you have to do it like that. If the design itself is a single latch design, then we have to use the previous mechanism. So, in both way we can have this latch based design. So, we can frame scan chains like this. There are several rules for this LSSD designs, like all storage elements must be polarity hold latches. So, this is one requirement. So, you cannot keep any storage element as normal latch, because then this scan chain cannot be framed. The latches are controlled by two or more non-overlapping clocks, this C1, C2, A, B, like that. A set of clock primary inputs must follow three conditions. Okay. So, if you any set of clocks you take, that they must follow these conditions. The all clock inputs to SRL must be inactive when clock primary inputs are inactive. So, there should not be any other clock coming to the flip flop or coming to the latches. Okay. So, only the primary clocks that we have, so they should drive these clock inputs of SRLs. The clock input to any SRL must be controlled from one or more clock primary inputs. So, there should, so again the thing is that every clock input of an SRL has to be controlled by some primary input. And second thing is that no clock can be ANDed with another clock or its complement. So, if you AND, then there is a problem, because the operation becomes difficult to predict, like when this clock signal, how to enable it, how to disable it. So, that logic becomes complex. Many times what happens is, for the for designing purpose, so we put some logic on the clock line. So, do some ANDing of clock signals, so that when both the signals are active, then only this will be active, like that. But it should not be done here, and ANDed particularly has to be avoided, because ANDing means they are overlapping clocks. So, it will be active only when both the clocks are active. So, if you are taking a if you do an ANDing, that means that line output is going to be an ANDed operation. So, that will be active only during overlapping clocks. So, we do not want any action, we do not want the clocks to be overlapped, because in that case the operation becomes unpredictable. Then clock primary inputs must not feed the data inputs to SRLs either directly or through combinatorial logic. So, this clock primary inputs, it should not be connected to the DI input, for the same reason that in that case the data input will also change when the clock input is changing. So, when clock input is changing, if data input changes, then of course, there may be a setup hold timing problem, or if it is via through combinational logic, ending with say some logic operation around clock and then applied to the combination, then applied to the SRL data input, then also the same problem, that during the clock is during the when the clock is active, the data input may flicker. So, as a result, the operation may be problematic. Each system latch must be part of an SRL, and each SRL must be part of some scan chain. So, it says that there should not be any latch left as it is. Okay. So, that is one part, and also each SRL, each latch must be part of this, they must be put into some scan chain. So, no latch remains uncontrolled. So, that is the whole thing, the no latch remains uncontrolled. A scan state exists under certain condition. Each SRL or scan out SO is a function of only the preceding SRL or scan input SI in its scan chain during the scan operation. So, this is the first condition, that in for any scan cell, it is not its content in the next clock cycle, it is dependent on the content of previous scan cell only. So, it is or from the scan primary input. So, it is only on those two parts the scan out of a scan out will depend. So, it is not that it depends on some other logic and all that. So, the scan chain is actually from one chain to another chain, the connection is a straight connection, one flip flop to another flip flop on a chain, or sorry, one latch to another latch on a chain. So, that is a straight away connection. So, there is no logic in between. So, it is not a function of something else, and all clocks except the shift clocks are disabled at the SRL clock inputs. So, this is also necessary, because when we are shifting, so all other clocks must be disabled, only the shift clock should be applied. So, next the partial scan design. So, in partial scan design, what we do is that we will be considering only a subset of latches or flip flops for putting onto into this scan chain. So, the problem with full scan design is that we cannot it may not be possible to put all the flip flops or latches onto a chain. So, partial scan design will try to resolve this issue and try to come up with solutions, so that we have less complexity. We have many of the design, all design criteria are met in terms of timing, in terms of power, in terms of area and all that. So, we will continue in the next lecture.